Good. Okay, Javier, I think we are going to start. I will introduce you. That sounds good. All right. Okay. Welcome, everybody. Thanks for coming here today. We're very thrilled to have this day the almost last speaker of the seminar, which is Javier Civera. Javier is a full professor at the University of Zaragoza, where he teaches computer vision, machine learning, and SLAM. He currently leads a research group composed of 5 PhD students and 3 postdoc students. He has co-authored over 100 scientific papers in computer vision and robotics, accumulating over 10,000 citations on Google Scholar across 20 years of scientific career. He has been nominated twice in 2009 and 2014 for Best Computer Vision Paper at IEEE ICRA. His predoctoral work was nominated to the Robert Dylan Award for the Best European Robotics Dissertation, and he received the Knockoff New Generation Star Award at IEEE IROS 2024 for his research career. His work mainly focuses on 3D visual reconstruction and semantic understanding with several highlights across the research community. Javier Civera has also served regularly in additional editorial and program committees in robotics and computer vision, and since 2019, as an expert evaluator for the European Commission for Age 2020 and Horizon Europe calls, and since 2023, as Deputy Director for the International Relations at the Aragon Institute for Engineering Research. With that being said, thanks again, Javier, for accepting the invite. We're very excited to have you today, so please, the floor is yours.
Okay. Yeah, thank you very much for the invitation. You hear me okay?
Yes,
The sound
perfect.
is good. Okay, yeah. So as I say, yeah, thank you very much for the invitation. It's a pleasure to share some discussion with you. So yeah, the title of my talk is I title it like this because basically I've been having this thought recently that my uh, my line of work is basically 3D perception, SLAM, specifically mainly visual SLAM. And I have the feeling lately that all I do is just taking foundation models and try to put them in 3D. So this is why I thought, okay, this is the regular thought that I'm having. Let's talk about this. So yeah, I will start. I'm sure you all know about this, but this is the slide, one of the slides that I use with my master students to tell them about what is a foundation model. So a foundation model is a general purpose model that is trained in massive and diverse data, and as it is trained in this massive and diverse data, then we can use that foundation model in several tasks. Sometimes even as the foundation model is pre-trained, and sometimes fine-tuning it a little bit. So the thing is, these foundation models, to really generalize and show this zero-shot behavior, you need to train in really massive data, and the modalities that nowadays are available for this massive training are images, text, audio. So when we go to the 3D world, we don't have that much data. So all we can do is take these foundation models and try to project them and use them for our tasks. So basically, there are four tasks that I found them very useful, and the results have been very nice. And these are the tasks that I would like to share. So uh, open vocabulary, semantic mapping, visual place recognition, multi-view reconstruction, multi-view stereo, and camera single view camera calibration. So I will go over these tasks, and I will highlight how, yeah, there is this common point of, yeah, what I've done is taking these models and try to put them in 3D. So regarding open vocabulary, I know that in your group you have work also in this topic. So maybe you already know about this, but basically by open vocabulary we mean trying to annotate all the elements in a scene without being restricted to a closed set of categories. So semantic segmentation traditionally was addressed as a classification problem, and neural networks were trained specifically for classification for a closed set of categories that maybe 1,000, 10,000, or 100, but always limited. And this was a very, very limiting assumption. Yeah, because in the end, when you go in the wild and you go to a new scene, there is for sure many, many categories, many object categories that uh, you never imagined beforehand that you were going to face. So with open vocabulary, what you do is you annotate the scene with visual language descriptors that lie in an embedding that is joint. It is a joint embedding for visual features and language features. And then this you can always query these descriptors using language features, and you can do things um, like the ones you see here. So if you build a map and then you put this query where to see it, then in the map you have some places highlighted. Here, for example, a place to take a nap, and you have this sofa highlighted. Okay, this is very curious. I don't have this image here, but if you query a place to sleep, the sofa is not highlighted, and then beds are highlighted. So this is just an example that the language has these subtleties there. So it is a very, very interesting representation, not only because it is open vocabulary, but also because there is a lot of subtleties that are embedded into this representation, and that you can use to infer things about your map. So we did this work recently. We did it at 2024, and it was finally published, maybe a month ago at RAW. And maybe I'll start with a video of what we do. This is very illustrative. So you will see here in this video like an online map, right? And at any point you can query with text queries any element of the map that you like. This is the pre-segmentation we do of the map. I will go into that later. And yeah, this works. This video is actually recorded in real time. So these kind of maps you may have them available at real time. If you query bin, both bins are highlighted as you see. So this is pretty much the result that you can have. This chair is interesting. It is always highlighting just one chair, not the two of them, because one of them is incomplete. So yeah, in the chair that is not highlighted, part of it, the legs of the chair are not completed on the reconstruction, and in the end, where the camera is looking everywhere, and finally it sees the legs of the chair. In the end, it is both chairs are highlighted. So yeah, possibly now that's it. As we have navigated the scene, now the reconstruction is more clear. So you can see that, yeah, the results look pretty nice. These are actually a bit cherry-picked results. Not everything looks so nice. So this is what I will try to convey now. So this is the overview of the system. We basically rely on a SLAM module that is able to give us the trajectory of the camera in real time, and it is estimating a consistent, a global representation of the scene. We use actually a SLAM system based on keyframes. That means for the map representation, we do not take every frame of the camera, but just a few of these frames that we call keyframes that somehow summarize the scene. And then for each of these keyframes, what we do is we use SAM to segment this image. We are using an RGBD camera, so as soon as we have the SAM segmentation in 2D, we project these segments back into 3D, and we track them in 3D. And then for each of these segments, what we do is we try to compute one of these visual language descriptors. Here we wrote clip like the generic a generic name for these descriptors, but in reality we use clip, which is an evolved version of these clip descriptors. And here it is one of the main weaknesses of these foundation models, and this is why you need to do something to put them in 3D, and it is as images and text are the data sources that are massively available. All these foundation models are regarding images or text and not 3D maps. Okay, so what we do here, we need to do something to project this clip, this visual language descriptors to 3D. This is a problem. First problem that is kind of tricky is we have multiple views. So yeah, what do we do with multiple views? Okay, so if we have multiple visual language descriptors. So in this paper, we do something very simple, and is heuristically we try to get the best of them, right? And this is a challenge and a research line that we would like to pursue. If we have several views in which we see something, we would like to fuse the vision language descriptor and not just take one of them. And but yeah, there is challenge in the fusion because this representation, this vision language representation, is an embedding, right? And you would like to fuse the descriptors without getting out of the embedding, and this is not so easy to do. Okay, so this is the first challenge, and the second challenge is these vision language descriptors are trained in large databases of images and captions. So the caption typically refers to the whole image. So typically you have a vision language descriptor that describes a whole image and not the specific objects within the image. Okay. So what we do here to compensate for that is we take three patches in the image. So we take the whole image, then we take the sum segment that we want to annotate with this vision language descriptor, both segmented out. So these black areas here, it means that we want to annotate this door with this vision language descriptor, so we take the rest out. And in case the surroundings have some context that is important for the clip or the clip embedding, we also use this patch with the background of these objects. So we compute a clip descriptor for each of these patches, and then we try to fuse it into a single one. Okay, and here, yeah, what we observe is that this is quite needed. If you just input the whole image, the descriptor that you get refers to the most prominent object in the image, or maybe, yeah, like a whole concept of the image and not the objects. But if you put the object only, sometimes the context gives some information. So this is why we kind of fuse these three descriptors. Okay, so this is how we operate to annotate these scenes with these clip descriptors. So yeah, I was thinking now, if you have any question, just on the fly, maybe you can interrupt me as I am going into things that may be complex. So yeah, interrupt me whenever you want, and or you'd like some clarification. So one of the main contributions of our pipeline is that it is the first that it is open vocabulary with loop closure, so with global consistency. So you can see here one example of this loop closing. So here you see that when you go through a scene, you may have some drift in your camera trajectory. When you revisit one place, For example, the floor here, you see that it is duplicated. So you can use feature matching slam loop closer to close the loop, but then these instances are duplicated. For example, this screen here is twice in the map. Even if you correct it, you still need to fuse these two screens into one because it was one. So this we made a very simple strategy, which is when we have two segments that are very close, both in the space and in the descriptor dimensions, we fuse them. Okay, this was pretty nice, but we observed that it is not perfect. For example, this the floor here, it is a bit hidden, but you see the floor, we painted it in gray and in magenta or violet, and you can see here that in this right picture after loop closure, you can still see here the magenta and the gray. So the floor was not properly fused, and this is something that we are looking into because we discovered after working for this paper that not every instance is successfully fused after loop closure, so probably more clever strategies than these ones need to be done. Yes. And another part that we were not very happy, even if it made the job, is this clip merging. So here, the literature did several things. One of them was simply averaging the descriptors, which it looked like a very simplistic, right? Then there was this work of SG that they already incorporated some weights in order to do a weight average of these descriptors to get a final one. And what we did is one step further and do per dimension weights to weight these clip descriptors. So we thought, okay, maybe each dimension of this descriptor has a different meaning, right? They don't need to have the same scale, or maybe they don't need to be weighted in the same manner. So let's learn a weight per dimension. Okay, and this is what we did here. Yeah, I told you that we were not very happy. This is the part that we were not very happy. When you What we did is training this network that is the one that predicts these weights that we use to weight these individual descriptors. The problem here is that if you want to train this network supervisedly, you do not have ground truth for this clip embedding. I mean, you need to weight these three, but what is the ground truth for this one? You don't know. So in order to train this, what we did is use the clip embedding of the category of this object. If this is a door, we use this word door just to get this descriptor, and this is the one that we considered as ground truth. But this is very limiting, right? Because as I told you, the clip embedding, it is able to model subtleties like colors, like I don't know, like affordances, right? Actions, and all of this is somehow, or it may be lost here if you just train with this categoric label. This is one problem. And the other problem is that you are in the end overfitting to a closed set of categories. And this really looks bad, right? We are trying to do open vocabulary, but in the end, we end up training this network in a closed set of labels. And then we overfit to them. So this made the work for this paper, and you will see that it already improves on the metrics, but this part we are now working on it, and we believe that something better maybe can be done. Yeah. So these are the results that we got. So I put here all the numbers, but maybe I will go. Yeah, the main message is up here you have the runtime. So more or less you can see that the runtime, uh, we wrote here the average time per sequence, okay? Just to show that we are somehow among the cheapest, yeah, the cheapest approaches. But yeah, the processing is on average, all this processing takes 1 second as we do it in the keyframe. As long as our keyframe rate is within 1 keyframe per second, this can run in real time. Our experiments, we run it in real time, but yeah, with this disclaimer, right? That we rely on a SLAM system that is taking keyframes. The tracking of the camera is made on a separate thread so that the tracking of the camera can be made at 30 frames per second. And then we do all this processing to get open vocabulary labels in the keyframes only. And there we can run at 1 keyframe per second, which is quite reasonable. It's close to the keyframe rate that every SLAM system is using. So this yeah, works quite rapidly, and you can see that more or less we are better than other baselines out there. One thing that we also saw in this work is that the metrics are quite low. So this is, we evaluated, evaluation is kind of tricky in these open vocabulary setups, right? Because again, you do not have the ground truth that your representation targets. So we did an evaluation based on, again, on a closed set of categories in annotated data sets with categories. And there we compute segmentation metrics, but you see this is mean intersection over union, and it is around 20-30%, which is quite low. Okay, so one thing that we saw is that this is still a very challenging problem. It is also, of course, very quite new, but certainly there is a lot of work to do. And we also saw that well, geometric accuracy is still important. Okay, one thing that we saw here is we just to prove generalization, we present experimental results with two SLAM systems, Gaussian SLAM and or SLAM 2. Each of them has different accuracies. It is interesting that yeah, in this one, Gaussian SLAM is better, and in this one, Orb SLAM is better. So yeah, in principle, yeah, for every data set, one SLAM system works better than the other, and yeah. But we saw is that the most accurate SLAM system, then it gets in general the best segmentation metrics too. So there is work to do both in the SLAM side, geometric side, and also in the representation side. Yeah, because in principle geometry matters. Yeah, we also evaluated with ground truth geometry, and results in general they are even better. Yeah, so definitely geometric accuracy is something. So this is yeah, this is what we learned with this work. It's a line of work that I find very promising. Yeah, I was not a believer on this semantic segmentation that they were doing with closed sets, and now I think this is something that it's very interesting, very relevant. So if you don't have any questions, I will jump to the next thing that we did with these foundation models. As I said, please
Javier?
interrupt. Yes,
Yeah.
Miguel.
It's Liam actually. On the previous slide, I'm just trying to understand the distinction between, let's say the third from last row, OVO mapping, and then the last two rows. So in the last two rows, you actually have like a SLAM system that's running, but in the third to last, you were just using ground truth for this, if I understand correctly. But then
That's it. Yes.
yeah, so how do you interpret the fact that in some cases, actually the performance goes up when your camera localization goes down? Like, What I mean is compared to ground truth, in some cases, your system with actually running a SLAM system, the performance on some of these segmentation metrics is actually better. How do you interpret that?
Yeah, well, the metrics are of course noisy, and well, here, for example, you see that in some cases the accuracy is lower, but actually the improvement is also very little. And here, this is the tail categories, metrics for the tail categories. So here the improvement is big, but these tail categories are actually quite noisy because these are categories that are hardly seen both in training and test. So yeah, these numbers here you can see actually that they jump. The range of variation in these numbers is larger than in the head categories, and this is actually the performance is also lower because these are categories that appear very rarely. Yeah.
Maybe just one follow-up, just to make sure that I understand. So
Yes.
the only distinction between the third to last row, where you have ground truth post, and the last two rows, the only distinction is the geometry, right? Like everything about the interpretation of the semantics is the same, or is there other differences?
No. That's it. Yeah, the semantics exactly the same. Metrics are exactly the same. The only difference is in the two last rows we run a SLAM system, and in the first row we just take the ground truth poses of the keyframes. Yes. Yes.
I also have a quick question, Javier.
Yes.
When you mention loop closures, are you just talking about the merging, or is it also that if the backend updates the pose of the keyframes you choose, you also trigger like a global update in your semantic map as well?
Yes, we do an update of the geometry and the semantics. So right now
Okay.
it is very simple what we do. We just take the post graph, okay? When we detect a loop closure, we correct the post graphs. As the poses of the keyframes are updated, we also update the point clouds that are attached to them. So the point
Okay.
clouds, we attach them locally to every keyframe. And then when we have the point clouds aligned there, we try to fuse these semantic entities that are close in space and close in descriptor distance. Yes.
Understood.
Yeah.
Thanks.
So something very simple. I'm sure also something more clever can be done. Yeah, I'm not sure how much you can gain by doing something clever in the loop closure. This is a discussion we had with the reviewers, so it would be nice that you have a more unified approach between geometry and semantics. But actually, I mean, local descriptors, local point descriptors, they are very accurate for geometry, right? And these open vocabulary descriptors are very noisy. So I still think the
Right.
best strategy is update differently the geometry and the semantics because, local descriptors are very good for geometry, very bad for semantics, and open vocabulary are very good for semantics, very bad for geometry. So, this is pretty much, my
Indeed.
thoughts about loop
Yeah,
closure.
I still find it very cool though. That's a problem I've been wrestling lately a lot, and most of these representations normally don't take that into account, right? Like as soon as they propagate into the map a keyframe, is even if the backend says that keyframe has been updated, is something that is not triggering the semantic level. So I found that still interesting. Thanks.
Yeah. That's it. This was our motivation was the same. Yeah, we observed that the rest of the baselines were not ready for that, so we implemented it. Yeah, but yeah, so far we did something really simple. Yeah, we'll think more about it. Yes.
Thank you.
Okay. Any other question regarding this topic? I'll jump to visual place recognition then. So in visual place recognition, is the problem as you may know of given uh, one image, try to know which place it is. Okay, and this is something that was first addressed with again local descriptors and back of words and geometric checking, as you can see in these two pictures. Yeah, looking at this, it looks like an easy problem, but then you can have examples like the ones below, okay? Where these are pairs of images that are from the same place, but even for us, you have to look twice, right? To get that they are the same place. A scene can have a lot of changes over time, and this becomes a difficult problem that is typically addressed now with deep learning, okay? And this is how it's typically addressed. What you do is you have one image of a place, you have a database of images that are geo-registered already. And what you do is you train a model and you encode each image into again, an embedding space, one descriptor, and you just do a KNN search over the descriptors of all these reference images. If you train this model so that it learns to be invariant to all these changes related to weather, to day night, to dynamic objects, then these descriptors filter out all this content and they end up having the main static content, invariant content of the scene. And then this KNN search, it retrieves the best candidate for this place, even if the visual appearance is quite different. Okay. So these architectures for visual place recognition, they are composed of a feature extractor and a feature aggregator. So basically, you use a backbone to extract features, and then as you want a compact descriptor, just for your KNN later to be fast, to be efficient, then you have to aggregate all these descriptor into a compact descriptor of some hundreds of dimensions and hopefully not more. So it is here where we one of our works here or our contributions is using Dino V2 backbone, and we also improved over this aggregator. Okay, so yeah, about Dino V2, maybe the only thing that is special is that back in the day when we did this in the Dino V2 paper, they say that it is such a strong representation that hopefully you can use it without fine-tuning it for the task. And we found it that at least in visual place recognition, fine-tuning it gives quite a bit of improvement. Okay, so we specifically in our ablation, we found that unfreezing the four last blocks of Dino V2, it improves quite a bit the final recall, the metrics. Yeah. So this is the only special thing we did. I will later go a bit into the architecture a bit more, but yeah, this was the main message. And here in the in this aggregator, we used optimal transport theory. So we were inspired because a lot of computer vision problems were using these optimal transport theories lately. And actually the aggregation of visual features can be understood as one of these transport problems. Okay, so you have a backbone that is producing features, and then these features you have to feed them into the dimensions of your descriptors that are like the consumers. So you can treat the problem as this traditional problem of optimal transport. And it actually the big benefit is that before using this optimal transport, the typical aggregator was doing a softmax over all the clusters. Okay, so the assignment of one features over the clusters have to sum one. So in this way, from the point of view of the features were well distributed, but not from the point of view of the clusters, because then if you have of the dimensions of the descriptor, if you just do a softmax, maybe you can overload some dimensions of the descriptor and some others, not a single feature is assigned to them. Okay, so if you do optimal transport tries to balance the production of features and then the consumptions of features by the dimensions, so the features are more spread in the dimensions of the descriptor, and then the descriptor is more effectively used. Okay, this is kind of a high level views of this contribution. So this is a bit going over the architecture, maybe too much detail. So as I told you, from Dynavi2, what we do is fine tune for the task and freezing the last blocks. Then this, I just told you, if you do a softmax, you are just considering this relation, but if you do optimal transport, you are considering also this relation. One thing that we also contributed is adding a cluster that we call dustbin, and all the features that are not important for a place, we make the network learn that they have to throw them away there. And then this dustbin, we never use it in the final descriptor. So we learn that some image content like the sky is useless. You have sky in every place, so it doesn't tell you anything about place recognition, at least in our datasets that are outdoors. And yeah, we use for this optimal transport, there is an algorithm that is the sinkhorn algorithm. This is the one we used, and this is why we call this salad, because we use the sinkhorn algorithm for locally aggregating descriptors. We also did, this is something that gives you more compact descriptors. The dimensionality of the final descriptor may be high because you are projecting these features into the dimensions of the descriptor. So the final descriptor, the size is the number of the clusters you make times the number of these, times the dimensionality of these tokens. And this is too much, but you can project them to a lower dimension, and this, we found that it works well and reduces a lot your dimensionality. We also use the global token of Dynavi2 to add more context, and this is just it. One thing that it was very nice is that visual place recognition models, starting from Dynavi2, they converge very quickly. So for our results, we never trained for more than 30 minutes in a single GPU. So yeah, contrary to other tasks that may need more training, for BPR we found that it is not much needed. And we achieved big improvements. So in particular, I'm highlighting these two because these are the two that are less saturated. You see, this other recall is 90 something. This is smaller, and these are the ones where we got a big jump. And this is a visualization of the features that are aggregated in the descriptor. And you see all that is blue. These are features that goes to the dustbin, and the descriptor is not using them for recognition. And you see skies, roads are filtered out because they don't offer anything. They are everywhere outdoors, so they are not discriminative for the place recognition. And there is a big focus on distant buildings, because this is very identificative of a place. Like these closer walls, if you take another image, possibly they have this projective distortion, right? So the features change a bit, but these distant ones, they remain quite invariant for a big motion. And our assumption is that it is focusing on far elements, because of this. And well, these are some qualitative results. You can see that across season or across viewpoints or across day and night, this works quite well. And one thing that we saw here is that I showed you some improvement in the metrics. We explored a bit more carefully where the metrics, what was the failure modes, right? And what we saw is that somehow when it was failing, this is the network says that this is the closest image. What we observed is that really the closest image was not far. So the third retrieval is actually the closest image, but it's not that bad. And actually, these images, they are marked as not the same place, because typically in this field, the threshold for same place or not is 25 meters, but they are actually quite close also. So our intuition is that what we needed to do is just do a better training, just to get these ones here. And yeah, that the network was the result of our visual place recognition was close, but not there, but not totally wrong. Okay. So, and actually what we observe is that what we need to improve is what we call the geographic distance sensitivity. So this concept, what we thought is that if we put in one axis the geographic distance between places, and in the other axis the descriptor distance, what it is happening is this thing. If you put here the distribution over a lot of images, this curve, we would like to be monotonically increasing, right? So that images that are very close and have small descriptor distance, they are very close in geographic distance, and the same, that the distance correlates very well with the descriptor distance, and that it was happening that it was not. So we end up with something like this, and we would like something like this, like a better correlation in the sense of having a bigger slope and a smaller dispersion. And this is, of course, up to a threshold where you cannot see common areas, right? If you, in the end, if you increase the distance, you are going to end up in another street. There is no visual content that relates these two places if you are in different streets and you do not have visual overlap. So here, it doesn't matter anymore if if your correlation is lower. Okay. So this we also, I mean, you can formulate it statistically. You want your expectance, the expectance of this difference to be as small as possible, and also the variance to be as small as possible. And yeah, we devised an algorithm for what we thought is, okay, we need better training samples. There is a thing in these visual place recognition approaches, and it is that they are trained using contrastive losses. So you need to find pairs or triplets or images of different places. But you see, the number of combinations of images that you can do is huge. It scales up quickly, so you can choose your training pairs or your training sets from all the combinations. And the best is to choose the most challenging one or challenging ones. So what we did here is our algorithm, what it is based on building graphs. So what we do is we take an already pre-trained visual place recognition model, and we select images. Each of these nodes is an image, and we only put an edge if they are very close in the 3D space. Okay. So we keep doing that. We select another set of images that are visually very similar to these ones, and we only add an edge if they are very close spatially in the 3D space. We keep doing that, and in the end we find we have a graph of places. Each of these nodes is an image. As I said, all of them, they look alike because we chose these images so that they have descriptors that are very similar, and they only have a link if they are close in the 3D space. So what we do now is, in this graph, we search for clicks, and anytime we have a click, we have a bunch of places that are very similar in appearance, like this one, and they are of the same place because they are all at a small distance in 3D. Then we remove this click and we look for another one that is not connected with the first one. And then what we find, this is a real example of the algorithm running. And then what you find is images that are very similar to these other ones, but actually they are of a different place, even if to our eyes they look so similar that you would think it's the same place. It's another place, okay? And we keep doing that, and then by doing that, we end up with a very, very difficult training batch that is composed of images that they all look very, very similar, but some of them are of the same place in rows, and in columns they are of different places. Okay, and this forces the network to really do its best, right, and try to focus not only on these distant objects or high level features, but more subtle details to see if the place is the same. And with that, the improvement is also quite large in these data sets that are not saturated. And yeah, these are actually results from the data. The previous plot I showed about these graphs, it was made up, but if we plot the real distribution of the distance in meters and the descriptor distance, when we do this mining of the training samples, the correlation goes up in the sense that the slope is steeper and the this dispersion is smaller. And it is particularly noticeable, this effect, in this Norland dataset. This Norland dataset I can I can show you now. It's this dataset where you have 4 sequences taken by a train in Norway in each of the seasons, in winter, summer, autumn, and spring. So you can see here that the images, they vary a lot. And one reason why this dataset is very challenging is because some places, this is a train going over most, crossing Norway. So many places it's hard to distinguish. This place here is the same as this one, but you see the differences with this other place are very subtle, and this is another different place that is possibly kilometers away. Okay. And yeah, this big improvement is quite noticeable. This is a video of this Norland dataset in summer. This is the retrievals in winter by the state of the art before these 2 works of us. And this is our retrieval, and you can see that it's much more stable. Green means good retrieval, red means bad, and you can see that it's more stable. And you can see the difficulty, right? There is a lot of aliasing. Many images, they really look alike. Yes. And yeah, actually, this is one of these tasks where I found the performance of these deep networks amazing. Yeah, because it really is a hard task, and little by little, even hard data sets like this one, they saturate. Yes. Okay, so this is all. Yeah, I wanted to say about this visual place recognition work. We are very happy because this yeah, we released the code and it's used quite a lot. So yeah, so I don't know if you have any question about this. No. Okay. Okay. Well, maybe a bit more quickly. I don't know which time did we start. Because yeah, I wanted to keep this to 50 minutes, as you said.
Yeah, we were a little late going.
Yeah, I think we can start wrapping it up. Javier, sorry, I know we started a little
No,
bit
no,
late.
no. It's okay. Yeah, actually,
Okay.
I was asking for that. Yeah. I
Okay.
can leave the rest. Yeah, definitely.
Okay.
Yeah.
Cool.
So I don't know. Yeah, if you have any questions or anything, we can. Yeah.
Amazing. Well, first, thank you.
Okay, thank you.
And yeah, we will open the floor for questions now.
Maybe I can ask a general question about, so like where do you see this field of visual place recognition like now? Is it, are we at a point where we can say this is like pretty solved for the actual use cases that we want to use this for? Or is there, do you think that there's still like major open questions, and that this is like still a very active and promising line of research and will continue to be for years to come? Like, what's your sort of impression of this research field, I guess, is kind of what I'm asking.
Yeah. This is an interesting question. Yeah, for a while I also asked myself, okay, data sets keep saturating, and actually, this field of visual place recognition for quite a while it was kind of detached of localization, and then this question was fair. I actually asked myself, is this really useful for some downstream task? So this is why we are very happy to see that in this BGGTS slam from Carlones group, they are using this visual place recognition model, deep learning model, for their place recognition, and typically back of words was still used. So one could think, okay, is this further research really needed in Islam? Well, it's used here. And then there is other question, and it is if the field is already mature and techniques are working very well. I can say that the performance is really impressive. So if you test these models in the wild, so if you take a picture, I don't know, of a place it's impressive how well so you fear your privacy actually when you test this. But one thing that maybe it doesn't appear much in these benchmarks is viewpoint changes. So I wonder if this is maybe still a challenge. So these data sets are all taken in roads or train rails where the viewpoint is very limited, right? And I don't know if this is still a challenge. And actually, one of these works, this work here that was presented in Europe's 1 or 2 weeks ago, this is around about relating aerial views with street level views, and these viewpoint changes, I think, they are still hard. Yes, so there may be some challenges still there. But it is true that for small viewpoint changes and only changes of illumination or day and night or seasons, the performance is impressive. I would say these changes are really well captured by today's models. Yes.
Interesting. Have people looked at like building geometric invariants into these models to explicitly capture like that robustness across viewpoint changes, or it typically is like more the approach that you're like, if I understand, more like directly just trying to solve the matching problem in image space?
Yeah. I haven't seen that. Not that I know of. So I haven't seen any paper that focus specifically on this problem of viewpoint changes. Yes.
Okay.
So yeah.
Cool, thanks.
Okay. So there's something online, but yeah, I think that's it, Javier. We're running a
Okay.
bit time, so I don't want to drag more of your time as well. Thank you very much. Sorry we started a
Okay.
little bit late, but it was
No,
great to
no
have you
problem.
again. Thank you. Thanks a lot for
Yeah.
making the
Nice
time.
chatting with you. Nice
All
seeing you.
right. Yeah, likewise. Take care of
Bye
yourself, all right?
bye.
Ciao.
Yeah. Have a nice day.